now that we know our way around in the complex plane. The next step is to figure out how to understand functions whose inputs and outputs are both complex numbers. So this week we get our introduction to the world of what I'll call complex functions, or sometimes laboriously called functions of a complex variable. One of the main things that we'll be trying to work out along the way are what information and understanding do we have from functions of a real variable that we develop up through algebra and calculus that is going to serve us well in terms of functions of a complex variable, and what do complex functions get to do that maybe their real valued analogs did not do. So the complex functions that we look at this week are going to be fairly straightforward, familiar examples of the kinds of functions that we first dealt with in the algebra curriculum up through high school. We're talking about linear functions, power functions, maybe quadratics. We'll look a little bit at square roots. These really basic, what we would call algebraic functions. And those are already, as you'll find out, going to be a wealth of interesting phenomena happening just with that class of functions that were relatively straightforward in the real valued case, and they can do some pretty cool stuff as complex functions. But next week, we're going to transition to the transcendental functions, the functions that are not algebraic that we learn in the secondary curriculum. We're thinking of the trigonometric functions, sine and cosine and tangent, and exponential functions, logarithmic functions. What do their complex function analogs look like, and how do their properties differ? That's going to be a next week topic, but first things first. This week, we want to study functions of a complex variable, rather elementary ones. And again, we want to take this Klein Plan B type of viewpoint with it, by which I mean we're interested not just in the algebraic properties of these functions, but also their geometrical properties. How can we understand functions of a complex variable as transformations of the complex plane? And how can we make use of that correspondence between the geometric perspective and the algebraic perspective to represent and to solve problems algebraically? So that's the goal for what we're going to do this week. Let's take a flyover of the important ideas and definitions and what some of the visualizations and tools look like in this area. First of all, just to reinforce this idea, a function of a complex variable, which I abbreviate as a complex function, is just a function whose domain is the complex numbers, or a subset of the complex numbers, and whose codomain, whose output, is also complex numbers. So we feed f a complex input, and it produces for us a complex output. Again, to kind of keep our notation straight between when we're talking about complex functions versus real functions, we'll typically use z as an input variable for a complex function and w as the output. So z goes in, w comes out. This is in contrast to for real functions in the standard curriculum we customarily use x goes in, y comes out, right? So this is one way that we're helping our brains to distinguish between the two types of functions that we're working with. So just a quick remark about domains. Of course, it's probably better to specify anytime we introduce a function what is the domain of its definition. This is a fundamental part of what it means to define a function in the first place, and not every complex function is going to have its domain be the entirety of the complex plane, right? Even in the real valued function cases, we had functions like the square root or the reciprocal where there were certain values that just didn't work by mathematical necessity. But also, we can restrict the domain of a function just by our own choice. Like maybe there are reasons, maybe in applications, for example, where we have a function that's representing a value of a cost that I'm charging for a product that I'm marketing, right? It wouldn't make sense for that input variable to be negative just because we can't have a negative price that we'd be charging people. So either by choice or by mathematical necessity, domains can be subsets of the space of definition on which mathematically the function resides. So for example, the function f of z is 1 plus z over 1 minus z. We could say that the domain of definition of that function is just the complex numbers whose modulus is less than 1. So we're choosing to make a restriction. That restriction would make the domain of that particular complex function look like the open unit disk centered at the origin in the complex plane. And that's not a choice that we would make for this function by mathematical necessity. There might be some other reasons, right? So this is good practice, and every time I teach an analysis-flavored course to in-service teachers, this is something that I try to stress along the way, that the domain of a function is inextricably part of the definition of that function. And so if I change the domain, but I leave the formula that defines the function the same, I've fundamentally changed something about that function. I've changed the ordered pairs, the input-output ordered pairs, which are the sort of universal way of defining what a function is. It's a set of input-output pairs where each input is associated only with a single output. So if I change the domain, I'm altering the inputs that are parts of those ordered pairs, and therefore I'm either including more or I'm excluding more than I were before. So the domain inextricably a part of the definition of a function. That's the philosophy that we'll take for our course. So now that we know what a complex function is, right? It's just a function that takes a complex number as an input and it spits out a complex number as an output. We want to do some algebraic stuff with that. And the algebraic thing that we're going to look at is what's the nature of the relationship between complex functions and real valued functions. So there's a two-way street that goes in between those worlds, and we're going to talk about that in the next video by studying what are the real and imaginary part of a complex function. And then we want to take the geometric perspective, by which a complex function is going to determine a transformation of the complex plane. So that's going to be our step 2 and our step 3 in our material this week.